Great, so I'm happy to be here and to tell you a little bit about satisfiability modulo theories, what's going on under the hood here. And I want to thank some of my collaborators who contributed to these slides. All right, so to give you a very zoomed out view of the world, right? For many centuries, philosophers have dreamed of this idea of machines that can reason, right? And this pursuit of this dream has occupied some of the greatest minds of all time. So in a very brief timeline, you can go all the way back to Leibniz, one of the founders of calculus. And he had this idea that eventually, philosophers wouldn't need to argue anymore. They would just say, let us get out our machines and calculate. And the calculation will tell us the answer to all great philosophical questions. Hilbert proposed the Entscheidungsproblem as the most fundamental problem in mathematical logic, which is, given a formula in mathematical logic, can you determine whether it's a theorem or not? And that seemed like a very exciting problem. And then, of course, Church and Turing, poured some water on excitement because they proved that actually this is not possible. There is no algorithm that can always determine whether a formula in logic is a theorem. And so that was sad, right? Well, Gödel was involved too, right? Gödel, Church, Turing, these people. But then, mathematics recovered, and they said, all right, maybe we can't do everything, but we can do some things. And one really nice step forward was Martin Davis and his work on the Davis-Putnam algorithm, which was ultimately trying to prove something about, again, prove some theorems, and in particular showed there's a decision procedure for Pressburger arithmetic. So a fragment of arithmetic, you actually can always tell whether it's a theorem or not, okay? So there are some places where you can answer this problem. You can't answer it in general for first-order logic, but you can in certain cases. So, but yes? First-order resolution? Right, so first-order resolution is a semi-decision procedure, so it can prove theorems if they are theorems, but it can't tell you if it's not a theorem. So that goes back to this Entscheidungsproblem, right? So first-order resolution is a semi-decision procedure for the Entscheidungsproblem, but it can't always give you an answer. So that's why it's a little bit unsatisfying. And I would say that, at the turn of the century, we were sort of in this place where many people felt that this idea of automated reasoning was kind of a failure. It was still kind of a cool theoretical problem, but not really practical for most real-world applications. And there seemed to be these sort of decidability and complexity barriers to making it really practical. Well, then something interesting happened, which we like to call the Satisfiability Revolution. And right around 2000, there was this huge step forward in the most fundamental automated reasoning problem, which is the Boolean satisfiability problem, where suddenly we had these solvers, or the SAT problem, that could solve real problems, right? And this was kind of surprising, because the SAT problem is sort of the fundamental NP-complete problem. So we know that in general, there's not an efficient solution unless P equals NP, but we don't expect that's true. So how could this possibly be true? Well, the important observation is that for practical problems that come from the real world, they typically do not exhibit this worst case theoretical performance. And this was a really sort of fundamental observation that has shaped sort of the next couple of decades of work. Now, about the same time, I was doing my PhD here at Stanford, and we were all excited about these new SAT solvers, and we said, hey, what if we could combine that with reasoning about first-order theories to do something, even more powerful than what SAT can do? And so satisfiability modulo theories was born. All right, so what is an SMT solver? The idea of an SMT solver is really going back to these ideas of the great philosophers. Can we have a general purpose logic engine? Can we build something that can solve a wide variety of problems practically coming from many different applications? And the idea very simple. Given some condition X, is it possible for Y to happen, right? This is the kind of problem that we can answer. And we want to be able to express these ideas X and Y in some very rich logical language, okay? So not just Boolean logic. We'd like to be able to talk about maybe arithmetic or arrays or data structures, bit vectors, machine arithmetic, all these kinds of things that show up in real computer systems. And so that's the idea. And by building these tools and having them work successfully, this is really changing the way that people are solving problems now. So it used to be, you would study your particular niche area, and then you would build some algorithm that was tailored for that area and maybe spend a whole PhD on that. And then you have your own custom little algorithm that works for your problem and kind of nothing else. And the new way of doing things is you spend maybe a few months figuring out how to translate your problem into the language of SMT. Then you just run this SMT solver. And what's interesting is not only does this take a lot less time, but the result is often better because the SMT solvers have been highly engineered. The theory solver, the theories that they include have been carefully crafted to be efficient. And so there are many examples where, the best custom algorithm is actually outperformed by a translation to SMT. So, the team at Certora, they're no dummies. They understand this, and so that's why they're using SMT solvers in the back end. So let me show you a little bit about how it works. So this is kind of a high-level picture of the architecture of an SMT solver. So at the core, sort of running the show, you have a fast SAT solver for Boolean satisfiability. And it only sees the Boolean skeleton of the problem. So the problem could have a lot richer logic in it, could have arithmetic, bit vectors, other things. But you sort of hide all of that and look at just the Boolean structure, and that's what this part of the program sees. So what it's going to do is it's going to try to build an assignment for just the Boolean part of the problem. And then it's going to figure out which Boolean variables get assigned to true in order to satisfy that part of the problem. And then it communicates that information to the rest of the system. Now, the rest of the system, looks beyond the Boolean skeleton and is going to try to make sense out of these assertions. So you've got this sort of core part of the solver, and what it's doing is it's communicating with the SAT solver, and it's getting information about which assertions are true and false. And then it's going to sort of parcel that information out to the different theories that are supported by the SMT solver. And it also handles this sort of subtle thing I'm not going to talk about called theory combination, which is basically if each theory solver agrees that the formula is satisfiable, that's not quite good enough to know that the combined formula is satisfiable. They also have to agree on a few other things. It's a little bit technical, but this core part handles that as well. So then you have what are called the theory solvers. And the theory solvers, their job is just to understand their own particular theory. They don't have to worry about the Boolean part. They don't have to worry about the other parts. And their job is just to say, are the constraints in my particular theory satisfiable? Do they have a solution? But in order to be efficient, they have to have some other interesting engineering properties. So they need to be incremental, which means you can add a new constraint and very quickly ask again, is this still satisfiable? And you shouldn't have to recompute everything you've already done. They should be backtrackable, which means you can say, OK, checkpoint this set of assertions. I'm going to add some more, and I'm going to jump back to where I was before. And again, you should be able to do that without recomputing anything. They need to generate conflicts, which means they need to explain when something's not satisfiable. And there's this other thing called theory propagation, where they actually give information back to the SAT solver that I'll talk about more later. OK, so that's the big picture. And I probably don't have time to go through all of these slides because I included a lot. But I'll go through as much as I can, but we'll make these slides available too. All right, so the next thing I want to talk about a little bit is the theory solvers. So what is a theory solver? Well, given some logical theory T, It basically takes a set of literals. A literals is just a set of constraints with no Boolean structure. You can think of like x less than y less than z, z less than x, right? Those would be 3 literals. And then it checks whether this set has a solution or is satisfiable. And it's satisfiable if and only if there's some model that makes it hold. And a model is a theoretical construct that tells us that there's a solution. You can think of it as basically giving values to every variable in the formula. So what are some theories that we support in SMT solvers? Well, the sort of most basic one is called equality with uninterpreted functions. So this is just a theory that understands the predicate equality, and it also understands a function but we don't know anything else about the function. Okay, and what's nice about this, it's quite useful as an abstraction mechanism, right? So maybe you have some complicated formula, but it turns out that the reasoning that you need to check that formula doesn't need to understand the semantics of those functions. It just needs to do some basic pattern matching. So for example, the formula I have here, right, that has some complicated information about arithmetic with absolute values and multiplication and all this stuff, it's unsatisfiable. But in fact, you don't need any arithmetic reasoning to know this is unsatisfiable. It's unsatisfiable with any 3 functions that you could replace absolute value plus and multiplication with. So in fact, we can do that, right? We can add an abstracted version of this formula and check it with the theory of uninterpreted functions, and it'll tell us that this is unsatisfiable. So this is a useful construct. It's frequently used in verification to do abstraction, and there's very efficient algorithms for checking this theory. So another theory that's very useful, of course, is arithmetic. And SMT solvers include many algorithms for arithmetic, and often they have a sort of layered approach. So if your arithmetic is very simple, right, it's just a bunch of variables compared with constants, right? Or if it's maybe just a little bit more complicated, x minus y compared to a constant, these kinds of constraints are checkable in polynomial time, so you can have a very fast algorithm for that. Then you can have slightly more complicated things where it's still linear, and then you can use algorithms for linear programming, simplex algorithm for a Motzkin. And then, of course, in the most complicated case, you may have nonlinear arithmetic. And nonlinear arithmetic for the reals is still decidable, but it's quite complicated. There's been some interesting recent work with new algorithms for this that make it a little more tractable, but it's still quite, worst case, doubly exponential. So you have this sort of layered approach with all these different algorithms that can reason about arithmetic. And of course, reasoning about arithmetic is very important in many applications. Okay, another interesting theory is the theory of arrays. And this is very useful for abstracting, collections. Maybe you want to abstract memory. Maybe you want to talk about a specific array in a program. And the way this works is we have just a couple of axioms to axiomatize the idea of an array. So one is we have these 2 operators, read and write. So write is going to take an array, an index, and a value, and it's going to give you back a new array that's been updated with that value at that index. Okay, that's what the write operator does. And the read operator just gives you back the value at a specific index. So all you need to know about arrays is that if you read from an address that was written, you get back the thing that was written. And if you read from a different address, you just get back whatever was there before the write. It turns out that this is sufficient. Sometimes we also need this extensionality axiom that says basically 2 arrays are equal if each of their entries are equal. Okay, and there are several nice algorithms for deciding this theory. And you can try to figure out whether this is satisfiable, but I think I'll skip that for now. Okay, another really important theory is the theory of bit vectors or machine arithmetic. So it's like the arithmetic theory, but computers don't really work with real integers. They work with integers mod 2 to the n for some n, which is often 32 or 64, or if you're in smart contract land, 256, right? And to be able to reason precisely about that. And the theory of bit vectors does exactly this. So it can handle things like concatenating and extracting from bit vectors. It can do logical operations. It can do arithmetic operations, and so on. Okay, so again, I think I'll skip the example, but this is a very important theory, and it's supported by most modern SMT solvers. Okay, now I don't have time to tell you how these theories are all implemented, because it's, there's like, it would be multiple lectures for each one. But I will tell you how a very simple theory is implemented, just to give you a flavor. And this is the theory solver for difference logic. So in difference logic, we have constraints of the form x minus y has some relationship to a constant. Okay, and these kinds of things come up in applications with scheduling, for example. And we're going to allow x and y to range either over the integers or the reals. For integers, it's called integer difference logic. For reals, it's called real difference logic. And this will give you a flavor for how you build a theory solver. So one of the first steps is to sort of narrow your scope by rewriting constraints into a sort of a core set of operators. So here we can actually rewrite everything in terms of less than equal. How do we do that? Well, if we have equality, we can write that as the conjunction of two inequalities, right? If we have greater than or equal, we can just solve and switch it to get less than or equal. If we have strict greater than, we're going to first switch it to less than. And then less than, there's this trick. If we're in the integer domain, we can rewrite less than using less than or equal. If we're in the real domain, it's a bit of a pain. So what you have to do is introduce this delta, which represents a very small number. And you can write it this way, and then you have to do some extra work to figure out what value of delta ensures that you're still correct. So I'm not going to go into that, but you can read papers about it. Okay, so we can actually turn everything into less than or equal, so that's great. And then what we do is we have a conjunction of literals. Every literal looks like x minus y less than or equal to constant. And we can form a weighted directed graph with a vertex for each variable. So for each constraint x minus y less than or equal to c, we have an edge from x to y labeled by c. And then it turns out that the set of literals is satisfiable if and only if there's no cycle where the sum of the weights is negative. Okay, so you can try to prove that for an exercise. And there are a number of efficient algorithms for detecting negative cycles, so you can implement that, and now you have a decision procedure for difference logic. So let's look at an example. Let's say I have these set of constraints. So first thing I'm going to do is rewrite them. So as I mentioned, equality gets rewritten here. And everything gets turned into less than or equal. Now I can form this, this graph. And can anyone tell me if this is satisfiable or not?
It's satisfiable. You can go -3, -1, -4, +2.
That's right. So there's this negative cycle right here, -3, -1, 2. And that corresponds to three constraints, which if you sum them, you'll get something like, 0 is less than -1, right? And that'll be unsatisfiable. Great. Okay. So that's an example of how you can build a theory solver. And typically, yes?
Just for people who are outside this field, even in this simple example, if you try to enumerate, there are infinite numbers that you can try. So it shows you that there is something clever. We are not just trying to, if you just enumerate them, you will not be able to solve it.
That's right. That's right. And this is actually, the pattern I'm showing you here is typical of how you would build a solver for these different theories. Typically, there's some rewriting where you rewrite constraints into some very, very narrow form. And then there's some algebraic manipulation you do on those terms. And then there's some algorithm that is going to give you a solution if there is one. And that algorithm, typically it has some calculus, and you probably want to do some proof that shows that it's complete and so on. But for all of these, theories that I've shown you, there are papers that basically describe these algorithms, show that they're sound and complete. And so you really do have, a decision procedure for solving these things. Okay. So I know I started late, but how far should I go? Okay, so I want to tell you a little bit about, so that's about theory solvers, and the other thing I want to tell you a little bit about is how do how does the SAT solver and the theory solver communicate? Okay, and this is sort of at the crux of how SMT solvers were made efficient. Okay, so basically, it turns out that if I can solve, a problem about literals, I can also solve a problem with arbitrary Boolean structure. And one way to see that is I can just take any formula I'm given and convert it into disjunctive normal form. And then you can check each disjunct, which is a conjunction, and that's a theoretical proof that it's decidable. However, converting a formula to disjunctive normal form could be exponentially bad, right? So you don't want to do that. So what we want to do instead is exploit the power of these fast SAT solvers and somehow use that to do the Boolean reasoning. Now there's two main approaches. One is to just take your whole problem and somehow translate it into Boolean satisfiability, which you can do in some cases. This is called the eager approach. But most modern SMT solvers use the lazy approach, where you sort of incrementally do this back and forth between the SAT solver and the theory solver. So that's what I'm going to talk about. Okay, and what's nice about this is each part of the tool is doing what it's good at. The SAT solver does the Boolean reasoning, the theory solver does the theory reasoning, and this gives you, it's also very nice because it's modular. So if you want to add new theory reasoning to the solver, you don't have to change anything that's there. You just add this new theory module. All right, so there are several variants of this sort of lazy SMT approach, and one way to understand them is to reason about them at a slightly more abstract level. And so there's this very nice framework that was developed by Cesare Tonelli and his collaborators called the Abstract DPLL framework, which I'll show you here. So the idea is we're going to model a SAT solver as a transition system. And there's two basic parts to the state. There's this thing called a trail or truth assignment, which we'll label M. And it's just a set of things that are true, that we've assumed to be true. And then there's the formula that we're trying to solve, which we'll call F. Okay? And we can grow M either by making a deduction, where we figure out that a certain literal has to be true, or we can make a guess. Okay? And if we make a wrong guess, we'll have to backtrack. All right, so the states are either a fail state, which means we're done and it's unsatisfiable, or we have this pair M and F. M is a sequence of literals that are true, and also we have these decision points that tell us when we've made a decision. Yeah, I think I'll skip some of these technical details. And then we're going to and then we have a certain set of rules that we can use to make transitions. And the way we'll describe the rules is there'll be a set of premises that have to hold, and if the premises hold, then you can make some changes to M or F. Okay? All right, so the first rule is the rule that's known as unit propagation or Boolean constraint propagation. And it just says if I have a clause in my formula F that I'm trying to satisfy, it has some literals 1 through n, and the negation of 1 through n is already in M. So that means we've already made the assumption that literals L1 through Ln are false. Okay? So in our current context M, they're false, which means this last literal L has to be true if we have any hope of satisfying this clause, right? If everything else in the disjunction is false, the last thing has to be true. And so we're going to add L to our trail, to our set of assumptions. Okay, so this rule says if you've assumed everything but 1 to be false in a clause, then you can always just take that last literal to be true. Okay, so that's the unit propagation rule. We also have this decide rule, and it just says if there's some literal in the formula and we have not yet decided whether it's true or false, we can make a guess. And we're going to put this big dot here to show that this is a decision, not a propagation, right? So this is something where we've made a guess. We might have to undo that guess. Okay, there's a rule called fail, which just says if I have a clause that is false in the current model, M, and there's no decisions to undo, that means I've somehow reached a state where I know that the problem is not satisfiable. Then I just fail. And then we have this backtrack rule, which says, again, same case, I have a formula that's not satisfied, but I do have a decision. Then I can just backtrack to the decision, take the decision, and do the opposite, right? So I had made a decision that L was true. I'm going to backtrack and instead decide that L is false. Okay. I'm going to give you an example of all of this in just a second. This is a basic DPLL algorithm, but modern solvers are a little smarter. They use something called CDCL, which stands for conflict-driven clause learning, and so we need a few more rules to model that. So instead of the backtrack rule, what we do is when there's a clause that's not satisfied, we put it in this special state called C, which is for conflict. Okay, and then what we're going to do is we're going to try to learn something from this conflict. So what we do is we use this explain rule, and the explain rule basically says, okay, let's say the conflict is this clause L or D. Let's look at the most recent thing in the conflict and where did it come from, okay, which is this L. So that means L needs to be the most recent thing on the trail, that's what this says, of all the other literals. And then we look to see which clause did it propagate from, okay? This is the clause that it propagated from. And what we're going to do is we're going to do a Boolean resolution step with the conflict and the clause that it propagated from. This gives us another clause that's also false in the current trail, but it has sort of, you've gotten rid of some of the more recent literals. And what you're trying to do is you're going to try to get a clause in C that has literals from as far back as possible in the trail. What that's going to let you do is it's going to let you jump back farther in your search. That's what this back jump says, is once you get a conflict clause where all but one of the literals in the conflict are at levels above the current level in the decision trail, then you do the back jump all the way to that level, okay? I'll show you an example. Okay, so here's an example. So here we have a bunch of clauses. So I'm just using integers for variables. A bar means the negation of the variable. And so you can think of it as a conjunction of these disjunctions of variables. And this is a pure SAT problem. So we start, and we can propagate 1 because 1 is a unit clause, right? So 1 has to be true. So we put 1 in M. Now we can look at the second clause. We can also propagate 2, right? So now we have 1 and 2 are true. Now we can't propagate anything else. We have to make a decision. So let's just choose 3 to be true, okay? If we choose 3 to be true, we can propagate 4. We have to make another decision. Let's choose 5. We can propagate not 6. We can propagate 7. And now, so notice that we're propagating 7 because of this one. But now look, if you notice, this clause is not satisfied, right? Everything has the wrong value for that clause. So we have a conflict. So we're going to put that clause in our conflict bucket here. And then we're going to say, why did we get this conflict? Well, it's because of 7. 7 was propagated by this 157 clause. So if we do an explain with 157 and this, we basically get rid of the 7 and we get the other, everything else that's left. So we get not 1 or not 2 or not 5 or 6 is our new clause. And then we can explain that one based on 6, which came from this not 5 or not 6. So if we do combine this one with this one, we now get this, not 1 or not 2 or not 5. And now the not 1 or not 2 or not 5 has this property that all but one of the literals come from far back in the trace here. So we can back jump all the way back to where 1 and 2 are known, but 5 is not. So we back jump all the way to here and set 5 to false, okay? And then we can keep going. So that just gives you a little flavor of basically how these conflict-driven clause learning solvers work. All right, and there's a few more rules. You can learn new clauses, you can forget clauses, you can restart, and modern SAT solvers use all of these techniques. Okay, but what about SMT? Well, if you want to now see how this works for SMT, it's actually very similar. So the idea is now the numbers 1, 2, 3, 4, 5 are going to represent theory literals, not just Boolean variables. And we're going to add a few new rules, t-conflict, t-propagate, and t-explain, which I'll show you how that works. In fact, it's best to do it with an example. So here we have another example, and this is using this theory of equality with uninterpreted functions. And here, so each of these equalities is going to be assigned a literal. So this is 1. Since this is a disequality, it's the negation of 2. So 2 would just be f of g of a equals f of c. This is 3, and this is negation of 4. So c equals d is 4. Okay? All right, so we start off. We know this is the formula we're trying to satisfy. We can do unit propagation on 1 and not 4. So 1 is true, 4 is false. We have to make a decision, so let's decide that 2 is false. Now, now we've basically satisfied all of the clauses at the Boolean level. So now we go ask the theory solver, hey, if I set 1 to true, 4 to false, and 2 to false, is that okay? And it comes back and it says, no, that's not okay. And the reason it's not okay is because if g of a equals c, that implies that f of g of a has to equal f of c by functional congruence. So just 1 and not 2 is already enough to be a problem. But the most basic idea would be just to say, okay, whatever you gave me is no good, so I'm going to give you a conflict that's basically the negation of the current set assignment. So we learned that. We can restart, do some more work, and fail. However, you can do much better than this, and modern SMT solvers have several tricks. So the first thing is we're going to use an online SAT engine, which means rather than waiting until the SAT engine is done and has a model, we can actually stop it partway through and say, wait, stop, here's a conflict. Okay, so we're going to more tightly integrate the SAT solver and the theory solver. We're also going to have an incremental and explicating theory solver, which means we can accept these conditions or these assignments one at a time as they come in, and as soon as we detect a conflict, we can stop. And not only that, we're going to give back a small subset of the set of constraints that we've seen, right? So it could be the SAT solver gives us 100 constraints, but we know that 3 of those are unsatisfiable in the theory. So we're going to give back just those 3, and that makes a huge difference. All right, so let's look at the example using all of this. We start the same, we propagate, we decide 2, but now we can immediately do the conflict, and notice we're just going to give back 1 and 2, because we know that 1 and 2 are in conflict just by themselves. Okay, so we get a stronger conflict clause here. Then we can back jump, propagate, again find a conflict here. It turns out that there's also this problem. If g of a equals c and c equals d, then g of a equals d by transitivity, right? So 1 and 4 imply 3. So we also get a conflict there. All right, but there's one more trick we can do, and I know I'm almost out of time, so this will be the last thing, which is theory propagation. So theory propagation is a clever thing where the solver is not just passively waiting for information from the SAT solver, but the theory solver can actually push information back, right? So it can say, hey, I've seen a certain set of literals. I can conclude something about this other literal that I know you care about. So the idea is if the set of constraints that's seen so far in M entails some literal that's not yet assigned, but it appears in the formula, then I can push that right back to the SAT solver. Okay, and then you need some explanation when you see a conflict. But let's see how this works. So in this case, we again propagate 1 and not 4. But notice that if 1 is true and 4 is false, the theory can actually deduce that 3, let's see. No, sorry. It's going to do, first thing we're going to do is it's going to say, oh, if g of a equals c, I know that 2 has to be true. So I'm going to just push that directly to the solver and set 2 to true. Okay? Now, I also can deduce that 1 and 4 force 3 to be false. So I'm going to push 3 false to the solver, immediately get a conflict, and I fail. Okay? So now notice that in this example, I didn't have to do any decisions at all, right? The theory solver was pushing enough information to the SAT solver was propagating, and it just basically converged on the solution immediately. So this is actually how modern SMT solvers work. You've got this SAT solver, you've got the theory solver, they're communicating very tightly, and they can just prune a lot of the search that way, and this is one of the ways that they're very efficient. Okay, so I think I'm already over time, and this is a good stopping place, so I'll stop here.
I had a question.
Yeah.
Sorry if I missed this. I had to step out for a second. Can different theories share variables between them?
Yes.
Okay.
Yes, and this, I didn't go into this, but there's this other step called theory combination. So essentially what happens is each theory solver looks at the set of constraints in its theory, decides whether it's satisfiable, and if any one of them is unsatisfiable, the whole thing is, so you stop. But if everybody agrees that their set of constraints is satisfiable, then there's one additional step where you have to look at the variables that are shared among the theories, and you have to ensure that each theory has the same equivalence relation for those variables. Okay, so it can't be that one theory thinks they're disequal and another theory thinks they're equal. That doesn't work. So you have to do some additional work to sort of get them to converge on the equivalence relation, and then once you've done that, then you're done.
I have a question.
Yeah.
If I would be stupid enough, I could write my own, let's say, array solver by adding the read override axiom as an axiom, right, to modern solver. So how would be that in terms of performance? Because I would add quantifiers, right, and I would add stuff. Right?
This is a great question. So I didn't talk about. Yeah. Okay. So the question is, what if I just rather than using the built-in array solver, what if I just wrote the 3 array axioms? How would that compare in performance? So I didn't talk about quantifier reasoning, and in general, so SMT solvers can reason about quantifiers, but of course, once you add quantifiers, the whole thing becomes undecidable. And so the techniques for reasoning about quantifiers in SMT, there's a whole bunch of them. But they're all heuristic, okay? They're based on, e-matching and enumeration and counterexample guided instantiation, all these clever ideas, but they're all ultimately incomplete. So basically, if you introduce axioms for your theory, you're like stepping into incomplete land, and maybe it works great, but maybe you fall off the exponential cliff and it doesn't work, right? So it actually does work a lot of the time, but once things start getting quite complicated, the stability of the solver becomes a little bit more difficult.
The fact that you add it as an axiom doesn't help, right? So it's going to go through the normal path of solving a quantifier.
Right, right. Now, one thing you could do is rather than adding a set of axioms, you could maybe add a set of rewrite rules based on the axioms that somehow are convergent. We did actually experiment with that in an earlier version of our tool. But as far as I know, no tool supports that kind of extension right now. Yeah. Okay.
All right, thank you.
Great.